Welcome back to ECE 442-542. This session is a review for unit number 3, and our goals: one is to look at the process that will be used for unit number 3's quiz. This review is trying to get you ready for the quiz over unit 3, and unit 3 really is covering the material associated with homework number 3, and we're going to look at that in terms of region of convergence. What are the patterns, the location of the poles relative to those patterns, and the interval of support for x of n, or when is x of n defined for what values of lowercase n. Is x of n bounded or unbounded? And how do you compute inverse Z transforms when you have real roots or complex roots? And maybe you're asked for the structure of x of n, or maybe you actually have to find the partial fraction expansion coefficients and produce the exact expression for x of n. You need to be able to do both of those. And the last piece that we will talk about is really putting some of this together in terms of a input with a system. So can you find the output response, which I'm labeling y of n, given an input r of n. R of n now is some input structure. It's a step, it's an exponential, it's an exponentially damped cosine, etc. And you're given a state space representation, or you're given a transfer function representation, or an all delay block diagram of a system. Combine that with the input, can you produce the output response y of n, either the exact y of n or the structure of y of n? What's the process for unit number 3's quiz? It's open notes and open book. You can bring a Z transform table. You can actually bring both. You can bring the one for exam number 2, which has Laplace and Z transforms in the same row, which is useful for zero order holds, but that's for unit 4 essentially. Or you can bring exam number 1's table of Z transforms, but both of those you'll want to be able to use to inverse Z transform. You can bring a calculator, something to write with, but you're not allowed to talk or communicate with anyone during this quiz, either in person or remote. You shouldn't be searching on your computer. You shouldn't be using your cell phone during the quiz. After you've submitted your quiz, then you can use your cell phone to scan your handwritten notes or your handwritten solutions to the quiz, and you're not supposed to be sharing any of your work or answers before, during, or after this quiz with anyone else. Obviously, you share them with me through D2L. The topics for Unit 3's quiz is really what's on homework number 3 and anything associated with that. And in sort of 3 pieces, it's region of convergence, interval of support for x of n if capital X of z is the transform, and how do you find the inverse Z transform of capital X of z. Let's start with this region of convergence. What are the patterns and the time interval of support? Here I have really 2 different patterns shown. The one on the left is a pattern, and I've got quite a bit of coloring here. Hopefully you can decipher what I'm trying to mean by the colors. If you look at the green shading, that region of convergence, the shaded region is the region of convergence. That region of convergence is interior to all of the poles. The poles all live beyond or outside the region of convergence for the green shading. And notice what I've done in the series expansion for capital X of z. I've written it out in terms of x at time minus 2, z to the minus 2, so that ends up being x at minus 2, z squared, etc. But now look at how I have curly bracketed in green the terms that are associated with that region of convergence. That's the non-causal portion, or if you substituted a value of z that's in the region of convergence for any of these other terms in this series expansion, they would become unbounded. And in particular, you might try the extreme value, which is z is equal to 0. And now x of 1 divided by z, well, you can't divide by 0 and get something bounded. So all of those terms in this series expansion for capital X of z that live outside of the terms that are highlighted or bracketed by this green curve are going to have to be 0. Similarly with what I've done with the orange on the right region of convergence in the z-plane, the region of convergence now is outside of, or the poles are all interior to the region of convergence. And remember, poles cannot lie on or in the region of convergence. Here the orange is bracketing or emphasizing the fact that we're only getting the non-negative time-indexed values of little x of n. And that's the causal sequence. Compare that then with what I have now shown with the purple enclosed terms. And the purple now is a region of convergence that's the green, except I've now removed the origin. So 0 is not an element of the region of convergence for what I'm showing with the left. That means that you could have a finite number of non-negative indexed x's associated with this region of convergence. And that's a left-sided sequence. So a left-sided is more general than non-causal. Non-causal means that the indices are negative. A left-sided means that you can actually allow a finite number of non-negative indexed values of little x of n present in your z transform. The yellow highlight is, in fact, the case where now this region of convergence is associated with everything outside of the poles, except it does not include infinity. Infinity is not contained in the region of convergence in this yellow highlight, and that means you have a right-sided sequence as an option, or that can exist for a region of convergence that's outside of all of your poles, but it's also bounded in terms of it does not extend out to infinity. And that then allows you to have some negative indexed values of little x of n in your series expansion for the z transform of capital X of z. You can have a right-sided sequence that can be larger than a causal sequence, similarly to how you could have a left-sided which could be larger than a non-causal. So a causal is always right-sided and a non-causal is always left-sided, but a sequence, a right-sided sequence, is not necessarily causal. It could include more terms, and a left-sided sequence is not necessarily non-causal. It also could include more terms. Those are the two patterns associated with left-sided and right-sided. Left-sided again includes non-causal. Right-sided includes causal. We have the third pattern, which is now what we refer to as two-sided. Now we actually have poles. Some poles are interior to the region of convergence. Some are outside of the region of convergence. None are in the region of convergence. But with a two-sided region of convergence, or this, I should say, a annular region of convergence, leads to a two-sided time sequence, so that now x of n could be non-zero for n between minus infinity and plus infinity. So this donut region of convergence, not a disk and not a z-plane with a hole in it, but now we have a donut region of convergence, or an annular region of convergence. That leads to a two-sided sequence x of n. X of n is now non-zero in extent from minus infinity all the way to plus infinity. Now, whether or not the x of n is bounded or unbounded, or we have a bounded or unbounded response, depends on the modulus of the mode, and the modulus of the mode is just another way of saying the magnitude of that mode. You need to look at the magnitude of the mode and the interval of support, or the time index window. When is that x of n defined? Suppose now we look at the first case where we have a non-negative time indices that are present, or this is now corresponding to a causal sequence. Or now the interval of support is non-negative values of n, or that's the time index window when x of n is defined. Suppose we have a mode, or all of our, if we have a mode, let's just look at one at a time. The mode, let's say, has a magnitude of r. Now I'm saying that z is equal to r e to the j theta sub d. I'm now looking at the magnitude of z, which is the magnitude of r to the n, with n greater than or equal to 0. If that magnitude is less than 1, what's the response? Bounded or unbounded? That you need to be comfortable with determining. In this case, n is non-negative. Think of it as positive powers of n, and r is less than 1. Now just pick a convenient value for r, 1/2 squared, 1/2 cubed. That's shrinking, so you have a bounded response. What if the mode r for a non-negative time index was actually bigger than 1? So now we have a mode r that's bigger than 1 with n greater than or equal to 0. That corresponds then to an unbounded response. Let's say r is 3 squared, 3 cubed. That's going unbounded. With a non-negative time index, where those modes are located is going to influence whether you have a bounded response or an unbounded response. And you can correlate that. That's this orange region of convergence. You could correlate that with, is your unit circle actually belonging to or lying on top of or contained in the region of convergence? If that was the unit circle, your system would be bounded. Your sequence, time sequence associated with those modes of those poles would be bounded. Let's look at the other case, which was the leftmost region of convergence pattern. Suppose now we look at negative time indices, or a non-causal sequence. Now we're letting little n be negative. If the mode r is less than 1, let's say it's 1/2, and we raise that to the -1, raise that to the -2, we're now really flipping 1/2 or inverting 1/2, so now we have 2 squared to cubed, so that actually now corresponds to an unbounded response. And if r is bigger than 1, then we have a bounded response when n is a negative sequence. Again, you can look at the region of convergence and say, is the unit circle, does it belong on top of, or is it on the region of convergence? And if it is, if that blue circle now is the unit circle, all of those poles are bigger in modulus than 1, and that will then correspond to a bounded time response associated with that configuration of the region of convergence containing, or the unit circle lying on top of, the region of convergence. That's region of convergence relative to the unit circle, and bounded response and unbounded response. Let's now look at inverse z transforms. Here's an example. Suppose we have y of z is a ratio of polynomials. First, you want to check the roots of the denominator, and that's going to be influencing your modes. And whether you have real roots, then you have exponential response. Those could be exponentially decaying. They could be exponentially growing. If they're complex, then it's exponentially damped sinusoids, an exponentially damped cosine, an exponentially damped sine. If they were actually associated with unbounded modes, then they would have a modulus bigger than 1, and you would have an exponentially undamped sinusoidal response. But the key is looking at the roots of the denominator. Are they on the real axis, or are they off the real axis? If they are complex, then you have some oscillatory behavior. Suppose we looked at an example. Suppose y of z was given to you as z over a quadratic. If you factor that quadratic, you need to be able to factor the quadratic. And let's say now that the region of convergence is the magnitude of z is bigger than 1/2. That's consistent now with these roots. You have two poles. One pole is at 1/4 and the other one is at 1/2. If you were drawing this, you would have something like that, and your region of convergence would be beyond, and this is now in the z-plane. You now know that if you wanted to find the inverse z transform, you could do that by looking at y of z over z, which is now this 1 over z squared minus 3/4 z plus 1/8, equaling a1 over z minus 1/2 and a2 over z minus 1/4. So we take the partial fraction of y of z over z. We could solve for a1 and a2 if we wanted to. If somebody just asked us for the structure, then all you would have to say is, oh, I have an a1 and an a2, and you didn't ask me. If you just asked for the structure, you wouldn't have to find exact values for a1 and a2. If I ask you to find a1 and a2, you could use the cover-up method since they are distinct, or you could use any technique that you find more convenient. You could get a common denominator and equate coefficients, etc. But you should be able to perform the computations needed to find the numerical values for a sub 1 and a sub 2. Those a1 and a2 were on the real line. They result in an exponential decay because in this case the unit circle is lying inside the unit or inside the region of convergence, and those poles have modulus less than 1. you now have a bounded response for y of n. And what's the final value of y of n? As n goes to infinity, those exponentials vanish. Y of n is going to 0 as n goes to infinity. What if the denominator actually led to complex roots for this quadratic? You could now find that the magnitude, or you could find, let me just say that this can be written as in another form where you now have z minus the real part quantity squared plus the imaginary part squared of those two complex roots. And in this blue parameterized form of the quadratic, you can explicitly see that the real part is 1/4, and the imaginary part, you now have one above the real axis and one below. You have one in the first quadrant and a second pole in the fourth quadrant. I hope I'm remembering my quadrants properly. So this is the second quadrant and this is the third quadrant. We now have a pole, and you could then express that pole in rectangular form, having a real part of 1/4, an imaginary part of 3/4, or you could find the pole location in polar form. You could find the hypotenuse of that right triangle created by 1/4 and 3/4. R is now 0.7906, and that angle, theta sub d, is going to now be the inverse tangent of the opposite side of theta sub d over the adjacent side, 1/4. Inverse tangent of 3 ends up being 71.56 degrees, and that makes sense. 3/4 is bigger than 1/4, so you know your angle is bigger than 45 degrees. And R needs to be bigger than 0.75 because that's one of the sides of that right triangle, and you know that your hypotenuse is larger than either of those two sides. So now with the rectangular form, 1/4 plus and minus j 3/4, you could find it in rectangular form or polar form, and you might want to get comfortable going back and forth, because you can actually use the cover-up method if these aren't poles that are repeated and these two poles are distinct. You have one in the first quadrant and one in the fourth quadrant. You have distinct poles. You can now use the cover-up method and find K1 and its conjugate. You really just need to find K1. The other partial fraction expansion coefficient is the conjugate of that. You can now solve for K1 and determine what little y of n needs to be, but K1 can now be found from the cover-up method. Or K1 is now going to be, note that, and we'll do this in a minute, so let me just go ahead and say that K1 is going to be, in general, complex. It's going to have a magnitude and an angle. And if you've now found K1 and the angle, you can immediately write down what the inverse z transform of capital Y of z is. It's now 2 times the magnitude of that partial fraction expansion coefficient, K1, r to the n. The poles, again, were a distance r from the origin. Cosine of theta sub d. Theta sub d was the angle that the poles made, or the pole in the first quadrant made, with the positive real axis, plus the angle of K1. If K1's angle had happened to be negative, then it would be cosine theta sub d n minus that angle, let's say 10 degrees, n greater than or equal to 0. Why is that true? Well, let's just quickly convince ourselves of why you can go from a y of z equaling, and so now hopefully you see that y of z is in fact going to be that, and you can now inverse z transform that first expression, or in combination with the second expression, which is what we're going to do to find what y of n is in the time domain. Y of n is now, if you inverse z transform those two terms, you would have k1 times the root raised to the nth power plus k1 conjugate, that's the partial fraction expansion coefficient, raised to the mode, or times the mode raised to the nth power. What does that produce? Well, the first piece, k1, remember, is complex. This piece right there is actually k1 written in polar form. This piece is now the conjugate of k1 in polar form. That's times, or scaling, r to the n. Now I'm just looking at this piece right here. That's r to the n e to the j theta sub dn. And this second term is now k1 star r to the n e to the minus j theta sub dn. You may want to go back over this at a little bit slower pace. Now if we factor out the common factors, we have the magnitude of k1 that's common to both of those terms. We have r to the n common to both of those terms. And now let me combine the exponential pieces. And that's what this is. This is now e to the j quantity theta sub dn, that's picking up this, plus this piece, which is the angle of k1. Then we have this piece right there. And that's e to the minus j quantity theta sub dn plus that angle k1. Notice that our exponents are just negatives of one another, and that from Euler is just 2 cosine theta sub dn plus angle of k1. Remember, we're really just using cosine of x is equal to e to the jx plus e to the minus jx over 2. That's where this is coming from. Once we see that these complex exponentials actually collapsed down into a cosine, this 2 comes out front, we still maintain the magnitude of k1, we still keep this r to the n, we have cosine of the argument in the exponent, theta sub dn plus angle of k1 for n greater than or equal to 0. Let's now return to our earlier example and evaluate k1. We had y of z was this ratio of polynomials of z. We're now going to go ahead and write z1 and z2 as the two modes, or the two roots of that complex, or the quadratic that has complex roots. z1 is in the first quadrant, and z sub 2 is in the fourth quadrant. They are the same distance away from the origin, 0.7906, and they're at opposite angles, 71.56, or maybe I should say angles of opposite sign, and the other one is below the real line at minus 71.56 degrees. We can now partial fraction expand y of z over z. That's just z minus 3/4 over the quadratic, plus now we are saying, oh, we have one factor that's on, we have a partial fraction coefficient k1 on top of z minus z1, and we have the other one, which is really the conjugate of k1, k1 star, on top of z minus r e to the minus j theta sub d. To find k1, we can use the cover-up method. That means we multiply everything, both sides through, by the factor underneath K1, which is this factor z minus z1. That factor now is removed from that piece, and we're left with z minus 3/4 over z minus z sub 2, and that's K1. We evaluate that at the value of z that causes this factor to vanish, which is actually z sub 1, the pole in the first quadrant, or we're now evaluating z minus z sub 2 in the denominator at z equaling the value of z1, which is the first quadrant's pole. Substituting those values in and multiplying by a convenient value of 1, we end up with K1 actually being what we thought it might be, complex, and it's 1/2 plus j 1/3. You can write that in polar form because now this is going to be the magnitude of K1 and this is the angle of K1. We can now plug that into our partial fraction expansion. Inverse Laplace or inverse Z transform both of those terms gives rise to y of n being 2 times the magnitude of K1. Remember, this is the magnitude of K1. R to the n, that's associated with the poles, cosine of theta sub dn plus the angle of K1, which is 33.69. That angle, K1, needs to be the angle of K1 associated with the partial fraction expansion coefficient on top of the factor or the pole factor in the first quadrant. Now, that's a way to write that y of n in terms of just a cosine. It's a phase shifted cosine. You could also express that in terms of a exponentially damped cosine plus an exponentially damped sine using this trig identity of cosine A plus B is equal to cosine A cosine B minus sine A sine B, where in this case A is theta sub dn and B is the angle of K1. Doing that now shows that y of n structurally, if somebody said, what's the structure of y of n, you wouldn't have had to find K1 or its conjugate. You could have simply said, oh, that's alpha 1 r to the n, where r was the distance away from the origin of the poles, cosine theta sub d n plus alpha sub 2, and I would actually want you to find r and theta sub d. But you wouldn't have to find the alpha 1 and the alpha 2. This is now the structure. If I just ask for the structure, you would actually need to find the r, that's the pole location, and its angle, theta sub d, but that's all you would have to find. You would just have to find the modes associated with those complex poles, and then if somebody said, what's the structure? Now you can write down, oh, that's an exponentially damped cosine plus an exponentially damped sine. And the exponential damping is the same rate, it has the same r, and the angle, theta sub d, in the argument for cosine and sine is the same. Let's now look quickly at some questions that could be asked relative to problems like problem 4 on exam number 2, spring of 19, or you could look at other similarly formulated problems. But on the quiz, you need to sort of be able to solve various steps of this process. We will walk through maybe the entire process, but you should be able to work through the different steps at different points in the solution process. Here we're trying to find the output response given the system, and the system could be expressed as a state space representation, a transfer function, or a block diagram, and the input. Suppose we're given this diagram, an all delay block diagram, and somebody says, what's y of n given r of n? Well, you could now find the transfer function between r of z and y of z, or you could say, you know what, and maybe somebody says, what's the structure of y of n? Now you could say, oh, I know how to do that if I knew the state space representation. I could just look at the eigenvalues of the phi matrix or the system matrix. Here's x1 of n plus 1. Here's x sub 2 of n plus 1. We can now say, oh, our state space representation, we can immediately determine from this all delay block diagram x1 of n plus 1 is 1 r of n, 3/4 x1 of n, and plus x2 of n. x2 of n plus 1 is now minus 1/8 x1 of n and minus 3/4 r of n. This is now our phi matrix. This is our gamma matrix, and our output matrix, if we wanted it, is now some linear combination of x1 and x2, and the way that we labeled this all delay block diagram, y of n is in fact x1 of n, and so C, the output matrix, or maybe we called that H in the discrete time setting, is just 1, 0 as a row vector. If somebody actually gave you the transfer function, in fact what they would have been giving you is this H zi minus phi inverse gamma r of z. This is now the t of z. So they could give you the t of z, they could give you the all delay block diagram, they could give you this state space representation, but now, no matter what they've given you, let's say that they say, oh, suppose r of n was in fact 3/4 to the n for n greater than or equal to 0. And they say find the structure of y of n. Well, you could then, based on what we have, you could say, oh, all I need are the modes of that system. The system modes are in fact determined from the eigenvalues of phi, or they could be the denominator roots of t of z. Those are the same things. And if you found the transfer function between r of z and y of z, that would be the same as this t of z that we've now parameterized in terms of h, phi, and gamma. If we now find, in fact, the eigenvalues of phi for this system, we now look at the determinant of lambda I minus phi and set that equal to 0 to find the modes, the system modes, or the eigenvalues of phi are the system modes. In this case, then, lambda I minus phi would be lambda minus 3/4 minus 1, 1/8, and lambda. We now say, okay, it's the product of the diagonal terms minus the product of the off-diagonal terms, which is minus 1/8. This now becomes lambda squared minus 3/4 lambda plus 1/8. You could now put that into the quadratic formula and solve for that, or if you see that that now factors, you now see that we have one system mode is 1/4, one system mode is 1/2, and the structure of y sub n is now determinable once they've now told us what r of n structure was. The structure of y of n is now going to be a combination or made up of all of those terms. Lambda 2 needs to be 1/2 if lambda 1 is 1/4. Or now we could say the structure is one of those modes scaled by alpha 1, the other mode scaled by alpha 2, and the mode due to the input, which I think was at 3/4. That's now the structure. And in fact, if you needed to find y of n, or all these alphas exactly, you could find y of z is equal to t of z r of z, multiply t of z by r of z, and do the inverse z transform on y of z over z to find the exact values of alpha 1, alpha 2, and alpha 3 through partial fraction expansion. One more question could be, what's the final value of y of n? N is now positive in terms of the interval of support. All of these values, modes, have a modulus or a magnitude less than 1. They're all shrinking exponentially. The final value of y of n is now going to go to 0 as n approaches infinity. That's what you need to be comfortable with for the Unit 3 quiz.